Hello everyone. In the last video I talked about the fundamental theorem of calculus. In this video and the next I'm going to show you some applications of this theorem. Now if you are familiar with the fundamental theorem, you already know that it has two parts. We call them FTC1 and FTC2. In this video I'm going to show you how to use FTC1 to differentiate functions which are defined as integrals. So let's start. Differentiating integrals. To be precise, here we are differentiating indefinite integrals with a base point. The derivative of a definite integral is 0, so we don't need to worry about that. Okay, so we need some kind of function, so we need some kind of variable in the definition. Okay, so let's start with FTC1. So theorem FTC1. Let f be a continuous function Now this hypothesis is important. The function, the integrand function should be continuous on a closed bounded interval a to b, and let g be the function defined by this rule, g of x equals to integration of f of t dt from a to x, where x is any number between a and b. Okay, now that's an indefinite integral with a base point a. So here there are several things to notice here. I'm going to tell you after I write this statement. Then what happens? Then g is continuous on the closed bounded interval a to b, differentiable at the interior, so in the open interval a to b. And finally the most important one is this, g prime of x equals to f of x for all x in AB. As I said in the last video, you can actually increase the differentiability of g at the endpoints if we allow one-sided differentiation. And then you can write g prime of x equals to f of x for all x in the closed bounded interval a to b. So that's possible. Okay, now several things we need to read very carefully. So in this statement, what do you have actually? Remark. We need several things, actually remarks. So f has to be continuous, okay? F needs to be continuous on this interval a to b. So that's one thing. And the next thing is this. Notice when we define this capital G function, at the lower limit of this integration we have a constant, right? So the lower limit of this function has to be a constant, and the lower limit of the integration this is a constant. So when you differentiate a function that is defined as some kind of integration, and if you don't have a constant at the base, you have to change it somewhere so that you have a constant. Otherwise you cannot apply FTC1. Okay, that's one thing you need to notice. And the second thing is the upper limit is x. notice this function capital G that has input x, right? And then you have the same thing, you have x over there. So if you have something other than x, as sine x, cosine x, or x squared, or square root of x, right? Any kind of function of x, that's not FTC. Okay, so whenever you want to apply FTC, you need to have x over there if G is defined in terms of x. But you can still differentiate if this is a function of x. We're going to see how to differentiate that. The trick is to use chain rule. But you need to set up the thing so that you can apply chain rule. Okay? So the next thing is this. Three. The upper limit of this integration is x, not a function of x. Well, I mean x equals to x, I mean x is a function, it's the identity function, but what it means is if you have some function which is not the identity function, then you have the problem. Okay, so I want to make that comment here. So if the upper limit is some function of x, then we need to use chain rule first. So first we need to use chain rule to make it look like the FTC1 statement, and then use FTC1, okay, to use chain rule before applying FTC1. Okay, now if I combine all these things, actually like basically 2 and 3, you can have this last remark, which is pretty much said here. But notice g prime of x equals to what? F of x, right? But g is this function, so what it means is d dx of this integration equals to f of x, right? I just want to write this thing. So g prime of x is d dx of this, and that equals to f of x. So number 4 is this remark, d dx of integration of f of t dt. So when you integrate, you actually need to use a different symbol here, like t, and you have to keep x for this. Okay, now this guy equals to what? F of x. Something you should remember all the time, that this x, that x, and that x, okay, you need to have x, x, x aligned. If you have something here, say x squared or x cubed or sine x, you need to change that thing. We're going to see examples of that, okay? And yeah, and whatever you have over there, here, f will have that variable inside. That's another thing you should notice. Okay, so these are 4 remarks. You always need to remember these remarks. So remark 1 is you always need to say when you're applying a theorem, like just like the mean value theorem or intermediate value theorem or extreme value theorem, right? You always check the hypothesis. So same here, you always need to check the hypothesis. You need to say that your function is continuous on this interval, so you can apply FTC1. And then when you apply FTC1, you always need to notice that the lower limit is a constant. And then you need to notice that the upper limit is the variable that you are differentiating with respect to. And if it is not, then you need to change the thing a little bit. Okay, and if you differentiate this guy with respect to x, it is going to be f evaluated at x. It's not f prime. Notice the same f goes over there. Just the variable changes. Okay? Now example. For each of the following functions, find its derivative. All right. The first one is this t minus t squared raised to some power. Let's take just 8. Okay. And we need to have a base point, so let's just make it 7 and let's make it x. Okay. So that's my function. Notice if you integrate this thing, then the output will depend on what your x is. Suppose your x is 8, right? Then you are integrating this function from 7 to 8. But if your x is 10, then you are integrating this from 7 to 10, so that will give you a different number, right? So every time you change your x, it gives you a different number. So this integration is a function of x. And we are going to differentiate this function with respect to x. We want to know the rate at which it is changing, okay? Solution. So let's first use a symbol for this. Okay, let f be this function f of t equals to t minus t squared raised to the power 8. Notice t minus t squared is a polynomial, and if you take integer powers of polynomials, it is still a polynomial. So this function f is a polynomial function, and therefore it is continuous everywhere. Notice f is a polynomial function. It's a polynomial function, and hence is continuous everywhere. Okay. And why are we talking about continuity? Because we want to apply FTC1, right? Therefore, FTC1 applies to f. This function, right? And that means, what is the derivative of this? Thus, derivative of this integration of t minus t squared raised to the power 8 with respect to t from 7 to x. So that guy equals to what? Now look at this thing. You have x here, if you have x there, right? Then this derivative equals to what? This function, the integrand function, evaluated at x. So this is just going to be okay, so let me write it in one more line. So this is just going to be what? F of x, right? You have x here, you have x there, so this is going to be f of x, right? Now, what is f of x? F of t, if you use t as your input, then this is t minus t squared raised to the power 8. So now if you just write your input as x, then this is going to be x minus x squared raised to the power 8. So that's it. That's the derivative of this, of this function. Notice this lower limit, that constant, has no contribution to the rate. Yeah, it doesn't matter. So I could have started at 0. Still, the rate will be the same. Okay. The next problem is this. Will be a little bit different than this one. So here, we had things aligned, right? We just had x at the upper limit. So in the next problem, you're going to see something which is not quite an x, rather a function of x. So the next one is this. This is integration of ln of t with respect to t, starting from the 1 up to e to the power x. Okay. Solution. We'll follow the same pattern of writing the solution. So let's give it a name. Let f of t equals to ln of t. Then natural log is continuous on its domain, right? Which is 0 to infinity, excluding 0. Then f is continuous on 0 to infinity. Now notice whenever we want to apply the fundamental theorem part 1, notice the way we define the capital G function. That function went from a to x, right? But that x came from the domain of the original function, little f. Now what is the domain of the integrand function, little f, 0 to infinity, right? So my upper limit actually should come from this interval. Is e to the x coming from that interval? Yes, because e to the x is always positive. It's never 0, it's never negative, right? So that's fine. Okay, now we need to do something here. Okay. All right, so let me just introduce one more symbol here. Let u, the trouble is we don't have an x here, instead we have e to the x, right? So we need to actually make these things align. So let u equals to e to the x, okay? Then notice this derivative of this function ddx of integration of ln of t from 1 up to e to the x. Now that guy, I will just use my new symbol. So this is integration from 1 up to u, right? Okay, now what is the problem? You had here an x, but you don't have there an x, right? These two things should align, but it does not align. Now what can we do to circumvent this problem? Chain rule. Yes, okay. So notice we will just pretend this guy as an x and then differentiate with respect to that. This whole thing is just the chain rule thing. So I will write this thing as, notice this is differentiation of this whole function, right? So what I will do, I will differentiate this guy with respect to u. Okay, so derivative of integration of natural log from 1 up to u. Okay, that thing. But since see, this is not, we didn't have u, we had x. So by the chain rule times ddx of u. Okay, so this happens by the chain rule. Okay. Now, by the way, what is ddx of u? U is e to the x, so ddx of u is e to the x, right? So this whole derivative is e to the x times this thing. So let me just write it. So that means ddx of integration of ln of t from 1 up to e to the x. That guy is ddx of u is e to the x times ddu of integration of ln of t from 1 up to u. All right. And now we actually need to use FTC1 over here. Okay. Notice u equals to e to the x is greater than 0. What it means is this u is coming from this domain of f. Okay? Therefore, by FTC1, we have what? DDU of integration of natural log from 1 up to u. That thing is, do you remember? If you have u here and u there, then this is going to be, this is f of t, right? So this is going to be, okay, let me just write it in terms of f. Okay, so this is u, this is u. So this derivative of the integration will be f evaluated at u. Right? But what is u? U is e to the x, right? Okay, I'm going to do that, but what is f? F of an input is natural log of that input. So this is ln u, but ln u is what? Ln of e to the x, which is what? X, right? Natural log and exponential e to the x, they cancel each other. So this derivative is actually x. And therefore, the whole derivative is e to the x times x. That's it. Okay. Yeah, this is x. Okay. Therefore, this derivative is e to the x times x, which is x times e to the x. So that's how you find derivative of functions when the upper limit is not just an x, it's some function of x. Okay. The next one will have a little bit more complexity. You need to see all these cases. Once you know, so there are basically 3 to 4 cases. So actually this is almost it. The next one will be just a little variation of that. And the last one I'm going to do will have one thing you just have to notice. We tend to overread things. So that's the only part there. Okay, so number 3 is this. Find the derivative of this function. This is tan inverse, integration of tan inverse. Now this one is going from square root of x up to 2x. Ooh. So that's my function. Notice here several things. First of all, you don't have any constant at the lower limit. That you need to fix. Okay? And notice neither square root of x nor 2x, none of them are just x. They are some functions of x. So how to solve this problem? It's not hard. It's just the previous problem. You'll use that in pieces. So solution. So first let's call this integrand f. Let f of t equals to artan. Now notice artan is continuous everywhere. Everywhere. Then f is continuous everywhere. And hence FTC1 applies to little f. All right. Now, to save some writing here, I wrote the same thing many times. Okay, let's just call this whole function capital G. Let g of x be this integration of tan inverse of t from square root of x up to 2x. Okay. Now notice we don't have a constant at the bottom, so we need to actually include this. We need to make some constant at the bottom. Now notice this is a property of definite integral. If you have, I actually mentioned this last time, but I'm doing this again. So if you have an integration of a function from a to b, and if there is a number c in between, right? So you can just you write this as integration of f from a to c, and then this one from c to b, right? So first you integrate this part and then you integrate that part. So you can just write this. Okay. So here what do you need? We actually need a constant between those two, right? So what I will do, let c be a constant. Then I can write this g of x as this. This guy is square root of x up to c of, yeah, this is, let me just write f. Integration of f of t. So this is integration of f of t from square root of x to c, and then integration of f of t from c up to 2x. Okay. Now notice at this step you have a constant at the bottom, so that's fine. You can apply FTC1, but here you have a constant, but instead of having that at the lower limit, you have that at the upper limit, which is a problem, right? But we can actually solve this problem pretty easily using one of the properties of integration. And what is that? Yes, so if we flip the sides, the upper and lower limit, that will contribute a negative sign. Okay, so this is just negative times integration of f of t dt from c up to square root of x, and then plus integration of f of t dt from c up to 2x. Okay, so what property we are using here? The property is this: integration of a function from a to b is negative times integration of the function from b to a. If you swap the upper and lower limit, that will contribute to a negative sign. That's what it is. All right, so this is my function g actually, and I can apply FTC to this one and that one. So then you just follow the previous problem and solve for this. That's what it is. Okay. Now, let me just finish this problem. So what are we looking for? We are looking for g prime of x, right? Now, if you take g prime of x, that's going to be derivative of this plus derivative of that. Okay. Now, g prime of x hence g prime of x equals to negative times d dx of integration of f of t from c up to square root of x plus d dx of f of t, integration of f of t from c up to 2x. Okay, and you'll use chain rule and then FTC1 to find those two derivatives, and then you'll be done. Okay, now if I want to use chain rule, I need to change some variables. So let's call square root of x to be u, and 2x to be v. Okay. Now notice f is continuous everywhere. So this u and v, they are coming from the domain of f. So FTC applies to these situations. Okay. So then what is this? ddx of integration of f of t from c up to square root of x. So that guy, notice I don't have x over there, right? I need to have x here, there, and then I can write this equals to f of x. But we don't have x there. That's why we need to make that change of variable. So this is ddx of integration of f of t from c up to, now this is u. Okay, and then you apply chain rule. So this is ddu of this integration of f of t from c up to u times times ddx of u, okay, by the chain rule. All right, and this guy equals to what? We have u here, u there, then derivative of the integral is the integrand, which is f evaluated at u. Okay, so this is f of u times ddx of u. By the way, what is ddx of u? U is the square root of x, right? So this is 1/2 times x to the power negative 1/2, so 1/2 square root of x, right? And f of u is f of u. The function f is tan inverse of u, but u is the square root of x, so this is tan inverse square root of x over 2 square root of x. Okay, so we got this derivative, and similarly we need to get the other one, and then we'll be done. Okay, and okay, so we get this, and then ddx of integration of f from c to 2x. This is ddx of integration of f of t from c to v. V is 2x, right? And then this guy will equal to ddv of this integration of f of t from c to v times derivative of v with respect to x by the chain rule. Okay. Oh, sorry, I didn't actually mention here. So this is by FTC1. You always need to mention what theorem you're using. So this guy is going to be what? We have v here, v there. So this is going to be f evaluated at v. So this is f of v times ddx of v. ddx of v is just 2, okay, by FTC1. All right. Now what is f of v? F of v is tan inverse of v, and we have this 2. But what is v? V is just 2x. So 2 times tan inverse of 2x. Therefore, g prime of x, that was the question. Therefore, g prime of x equals to negative of this derivative. So this is negative tan inverse of square root of x over 2 square root of x, and then plus 2 times tan inverse of 2x. That's the derivative of this function. Good? Okay. So now the last problem is this. Find the derivative of this function. Let's say 0 up to x, and then x squared sine of t square dt. We need to find derivative of this function. So what should you do first? You have a constant at the bottom, you have x on top, pretty good. Can we just take derivative right now? Let's see. So solution, let's call this function g, okay? Let g of x equals to this guy. Notice there is something going on. This integration is happening with respect to what? T. So anything that is not a function of t is a constant here. So x squared, since x is not a function of t, it's a constant here. And since it's a constant, if you have a constant factor, you just can factor that out, right? So that's the thing here. See, I mean, many people just don't notice that, and then they apply FTC right at the beginning. But no, you cannot apply FTC right from the beginning. So this is then g of x equals to this x squared times integration of sine of t squared from 0 to x. Okay, and why is this happening? Since x is not a function of t. Okay, and that means if I want to differentiate this, we have basically two functions. This is one and that is another. We have product of two functions, so we have to use the product rule. Okay. Therefore, g prime of x. So first I will differentiate x squared, that will give us 2x, and this part will remain as it is. Integration of sine of t squared dt 0 to x. And then x squared will be a factor, but then we need to differentiate this guy, sine of t squared dt from 0 to x. Okay. Now tell me, is sine a continuous function? Yes, it is. It is continuous everywhere, right? So we can apply FTC1 there. So this derivative is 2x times integration, sine of t square from 0 to x plus x squared times. Now this is you have x over here, x over there, right? So the derivative of the integration will be the integrand evaluated at x. Okay, now what is the integrand? Sine t squared. So you have to replace t by x. So then this is going to be sine of x squared. Okay, don't forget that part. So x will just replace t, but you do not replace the square. You need to have that square. Okay, so this by FTC1, since sine is continuous everywhere. Okay, so pretty much that's how you differentiate integrals. There are not much techniques. Yeah, but I'm going to solve 3 more problems. One of them will be derivative question, but asked in a different way. So sometimes people just freak out looking at that question, but it's the same thing. So I want to show you that you can see this thing in a different form. And the next thing is, next problem is this. You have a relation And then you have to evaluate your function at some point, which seems crazy, but then you can do that because you have FTC. And the third one will be a graphing question. I'll give you a graph and then I'll ask you two questions. One, give me the intervals on which it is increasing. Give me the interval on which it is concave, up or down. So that's it. Okay. So we'll pretty much continue this thing in a different way. So the next problem is this. Evaluate the following limit. Now what is this limit? This is the limit of 1 over h times integration of this function 9 plus 4 t square. Integration of this function with respect to t. Where should I go? So from 2 up to 2 plus h. Okay, and h approaches to 0. So that's my limit, and I need to figure that out. All right. Now, how scary does it look? At first, it seems pretty scary, right? But what is even worse is some people actually forget that there is 1 over h. So I have seen these things many times. People argue this way. Since h is approaching 0, 2 plus h is approaching 2. But then this integration is happening at 2, right? Because you are going from 2 to 2. So there is no interval. You don't create any area. That means this integration is 0. Well, that's a legitimate argument. But the thing is, this function is not just that. You have an 1 over h hidden. Then according to your analysis, this becomes a 0 over 0 because h is approaching 0, right? So on top it is 0 and at the bottom it is 0. Now this is a really bad situation for limit. If you have 0 over 0, many things can happen. It can happen that your function does not have a limit. It can happen that it has a limit. Okay. It can happen that it diverges, it goes to plus or minus infinity. Okay. So the thing is, it is inconclusive. If you have 0 over 0, it means nothing. It means your analysis fails. Try different analysis. Okay, that's what it means. So if you look at that function, don't go to that 0 thing. But this looks pretty familiar to something we have seen yesterday. And we have seen that several times. That actually represents something. The change in the function capital G, right? So that's the change. And then if you divide this by h, this is actually the difference quotient of the indefinite integral. That means this is just derivative of this integration at 2. That's what it is. I'm going to write the solution in detail, but yeah, that's the message you should take from this problem. Let's give this guy a name because we need to write it down many times. So let's just call this, let f of t equals to square root of 9 plus 4t square. Okay. Now notice 9 plus 4t square is a polynomial, and a square root of a polynomial, that composition, square root is continuous on its domain. And this composition therefore is continuous on its domain. But the domain is everything because 9 plus 4t square is always positive. Okay. Then f is continuous everywhere, and hence FTC applies to f. FTC 1. Actually, both of them applies to f. Applies to f. I'm just writing FTC 1 because we are dealing with FTC 1 now. All right, now we need to define this function. Let g be this function. We need to start from a point, a constant, a fixed point, a base point. Okay, so let's call this guy 0. Okay, so this is integration of f from 0 to x. Okay, where x is any real number. Real number. Okay, but then can you write this guy in terms of g? Notice what is g of 2 plus h? Then g of 2 plus h is integration of this function from 0 to 2 plus h, right? And g of 2 is what? Integration of this function from 0 to 2. Okay. Once again, we need to use the that property of definite integral, that you can actually write this as a summon. So then, and hence, okay, g of 2 plus h minus g of 2. So that guy is integration of f from 0 to 2 plus h minus integration of f from 0 to 2. Okay, but this thing, this is 0 and this is 2. Say h is positive, right? H can be negative as well, no problem. So 0 to 2 plus h you are integrating. So then you can write this as integration of this function from 0 to 2 plus integration of this function from 2 to 2 plus h. Okay. So now this guy equals to integration of f from 0 to 2 plus integration of f from 2 to 2 plus h, but also we have minus integration of f from 0 to 2. Okay, but notice we can actually cancel these two. Right? They have same value with different signs. All right, so this integration actually is basically g of 2 plus h minus g of 2. Okay, I want to keep this function for a while. Okay, why should I actually write? I will write over here. Okay. Then if I divide, so okay, so what it means is I will write the right hand side first. So that means integration of f from 2 to 2 plus h equals to g of 2 plus h minus g of 2. And now to get this function, I just need to multiply this by 1 over h, which is dividing by 1 over h, right? So that means 1 over h times this integration equals to the difference quotient of g at h, right? This is the difference quotient of the function capital G. And then if we take limit as h approaches 0, this becomes derivative of capital G at 2. Okay, so that means limit h goes to 0, 1 over h f of t, integration of f of t from 2 to 2 plus h is limit of g of 2 plus h minus g of 2 over h as h approaches 0. That is g prime of 2. So what are we looking for actually? It says evaluate this limit. Actually basically it is saying find g prime of 2. Find the slope of the tangent to the graph of g at 2. the same question, right? The same question written in different language. Okay, so what is g prime of x? By FTC1, we get g prime. Okay, so let me just remind you what, since g of x equals to this, integration of f of t from 0 to x by FTC1, we have g prime of x equals to what? This is ddx of integration of f of f from 0 up to x, right? You have x here, you have x over there. So by FTC1, this thing equals to f evaluated at x. Okay? And then g prime of 2 is this is equals to f of 2. Now, what is this f function? F of t is square root of 9 plus 4 times t squared. So if I plug in 2 there, I get 9 plus 4 times 2 squared, which is 4. So 4 times 4 is 16. 9 plus 16 is 25. The square root of 25 is 5. Okay? That's how you find this kind of limit. These are derivative questions written in the language of limit. Okay? So, one more problem about finding derivatives. This is a pretty good problem. I like this problem. I actually like this one and the one I'm going to do now. So, let f be a continuous function such that it satisfies this equation. So integration of f from 0 to x squared, that guy equals to x sine pi times x. So that's my function f. No, that's wrong. That's the integration of my function f. So f is not given, right? The formula of f is not given. You just know that f is continuous. That's it. Nothing else. Now, if this is the integration of f, oh God. So this line is down. I should have written this at this height. Okay. So the question is this: find f of 4. Oh God. How are you going to find f of 4? Can you plug in 4 over there for t? No luck, right? Because you have still x on the other side. Yeah. So the key here is to actually get towards f, but the obstacle is you have an integration, right? And f is inside that integration, so you need to break that integration. You need to kill that integration, right? So if you want to kill integration, what's your tool? Derivative. Okay? So that's actually, this problem shows how powerful fundamental theorem of calculus is. You need to unwind that integration thing by differentiation, and you can do that because this function is continuous and because we have fundamental theorem of calculus. So that's the thing. Okay, so solution. since f is continuous, FTC1 applies to f. Okay, hence what do we have? We have this equation. These two quantities are same. These two functions basically are same. And since these two functions are same, their derivatives will also be same. So if I take ddx on this side, ddx on that side, that will be the same. Hence, ddx of this 0 to x squared f of t dt equals to ddx of x sine pi of x. Okay. Now, what is the derivative of this integration of f from 0 to x squared? Yeah, notice you cannot actually apply FTC1 directly at this moment. Okay. So I would like to do that straightforward, but I want to break it down. So now let u equals to x squared. Okay. Then ddx of ddx of integration of f from 0 to x squared, that thing is ddx of integration of f from 0 to u, right? But you cannot do that because you need to have the same thing here and there. So you are going to use chain rule. Okay, now this thing equals to ddu of integration of f from 0 to u times ddx of u by the chain rule. And then this is by FTC1, this is f of u. And derivative of u with respect to x is just 2x by FTC1. But what is f? We don't know, but that's fine. But u is x squared, right? So this is 2x times f of x squared. So on the left side, we get 2x times f of x squared. Okay? And on the right side, what do I get? I have product of two functions, so I can just use product rule. Ddx of x sine pi times x. So that's first you differentiate x, so that's just 1, so sine pi of x plus, then you differentiate sine pi of x with respect to x and you keep x fixed. So that is going to be cosine pi of x. But by chain rule, you need to differentiate pi of x, so that will give you a pi. So this is sine pi of x plus pi x times cosine pi of x. Okay? And you just plug in those values. Therefore, what do you get? 2x f of x squared equals to sine pi times x plus x times, pi x times cosine of pi of x. Okay. But what were you looking for? We were looking for f of 4, right? What should I plug in for x to make the input inside f to be 4? 2. Okay? So plugging in 2, x equals to 2 will give us f of 4. And notice the good thing is, once I plug in x equals to 2, I will plug in x equals to 2 everywhere, so there will not be any more x left. So yeah, it will give us a concrete value. We have 2 times 2 is 4, and then f of 2 squared is f of 4. So, and on the right side I have sine 2 pi plus 2 times pi is 2 pi, and then cosine of 2 pi. Okay, now what is sine 2 pi? It's 0. And what is cosine 2 pi? 1, right? So this is 4 times f of 4 equals to 0 plus 2 pi times 1. So that means 4 times f of 4 equals to 2 pi. Therefore, f of 4 equals to 2 pi over 4, which is pi over 2. So that's how we solve this problem. I like this problem. This is one of my favorite problems in this section. So this shows how powerful the fundamental theorem of calculus is. Even though you don't know what the function f is, you can sometimes get its value at some specific points. All right. So the last problem for today is a graphical problem, and it's not hard. It's a very simple problem. Let f be a continuous function on the interval 0 to 6, having the following graph. So let's take this. This is t-axis, this is y-axis. Let's say this is 1, and then 2, 3, 4, 5, and 6. And so 1, 2, 3, -1, and -2. So at 1 we have a local max. F of 1 is 3, so, and then f of 2 is 0. So it looks like this, and then at 3 it has a local mean. And again it's, so actually 3 is over there, so yeah, let me erase this part again. And f of 4 is 0, and at 5 we have a local max, and at 6 it is 0 again. So that's my function. 1, 2, 3, 4, 5, and 6. Okay, so this is my function f, and what I need to do is I will define the function capital G as the accumulation function. So let G be the function defined by this integration g of x equals to integration of f from 0 to x, where x is between 0 and 6. Now the question is, number 1, find the intervals on which capital G is increasing. Okay, so that's the first question, and the second question is find the intervals on which capital G is concave down. Okay, solution. Now for this problem, this is actually increasing and decreasing property of a function that is related to its first derivative, right? And concavity is related to its second derivative. So this is related to the monotone function video. If you want to brush up your knowledge, you can go to that. So what we need here first is to get the derivative of capital G, okay? So by FTC1, we have what? G prime of x equals to f of x, right? And what do we know? If derivative is positive, then function is increasing, right? Now from the graph, what do we see? We see that this function f is positive on the interval 0 to 2 and 4 to 6. That means G prime is positive on 0 to 2 and 4 to 6. And therefore, the function is increasing on 0 to 2 and 4 to 6, right? From the graph, we see that G prime of x, which is f of x, is positive on 0 to 2. Okay, so sorry, let me write this thing. It's positive if x is in the interval 0 to 2 union 4 to 6, right? Therefore, f is increasing, capital G is increasing on this interval. On the interval 0 to 2 and 4 to 6. Okay, that solves part 1 of this question. Actually, from here you can also get where capital G is decreasing. Notice f is negative on this interval 2 to 4, right? So G prime of x is negative on 2 to 4. That means capital G is decreasing on 2 to 4. And you can also actually answer from here at what x values does f have a local max and local min. Notice G prime of 2 is actually 0, right? G prime of 2 is f of 2, that is 0. And also G prime of 4 is 0. G prime of 6 is 0, but that's an endpoint of the interval, so it's not an interior point. Now notice on the left side of 2, function is positive, f. That means G prime is positive, so it is increasing on the left side of 2 and decreasing on the right side of 2. So G of 2 is a local max, right? Similarly, G of 4 is a local min. On the left it is decreasing, on the right it is increasing. So that's how we can actually, this question can be extended to finding local extrema, and you can do that similarly. Okay, now to get the concavity, we need to get the second derivative of G. Now G double prime of x, that is f prime of x, right? Now, if the second derivative is positive, that means capital G is concave up. If it is negative, that means it is concave down, right? Now, capital G double prime is negative, that means f prime is negative. That means f is decreasing, right? So in other words, we actually need to figure out where f is decreasing. So from the graph, we see that f is decreasing on which interval? So on 0 to 1 it is increasing, and after that from 1 to 3 it is decreasing, right? 1 to 3. After that it is increasing from 3 to 5, but then 5 to 6 it is decreasing. So it is decreasing on 1 to 3 union 5 to 6. Okay, hence G double prime, hence actually the second derivative of G, which is the first derivative of f, is negative on this interval 1 to 3 union 5 to 6. Okay, and therefore capital G is concave down on 1 to 3 and 5 to 6. Okay. And notice once again here this question can be actually extended to ask on which intervals is capital G concave up. So capital G is concave up if G double prime of capital G double prime, which is f prime, is positive. That means f is increasing. Now from this graph we can see f is increasing on 0 to 1 and then 3 to 5. So capital G is concave up on 0 to 1 and 3 to 5. And then you can ask, what are the points of inflection? The first one will be 1, right? Because on the left side of 1 it is concave up, and on the right side of 1 it is concave down. So concavity changes at 1, therefore 1 G of 1 is a point of inflection of the function capital G. And also what happens at 3? On the left side of 3 it is concave down, but on the right side of 3 it is concave up, right? So at 3 you will also have a point of inflection. Okay, and also at 5, because on the left side of 5 it is concave up, but on the right side of 5 it is concave down. So 3 points of inflection. Okay, all right, that's the end of this video. I hope this helps, and this actually ends our problem solving on the first part of fundamental theorem. And if I have time I will make another video focused on the second part of the fundamental theorem, and we'll try to solve some problems. Some of those problems actually have applications in science and engineering. For example, in physics, say a particle is moving along a line, and if you know its velocity function, then you can find the distance it traveled in a given time interval, say 5 minutes or 10 minutes. You can do that. Or say water is draining from a tap, and then you know the rate at which it is draining, then you can actually use the second part of the fundamental theorem of calculus to find the amount of water that actually has drained in a given time duration. Okay, yeah, I hope to make that video pretty soon, but I cannot promise. Anyway, stay safe and see you next time.